Following on them from the previous two videos where we've looked at sp3 and sp2 hybrid orbitals, it's time to look at sp hybrids and see how they form and the type of bonding. If you'd like to download these slides, please go to the website and you'll be able to download them there as a PDF. So let's do a quick recap of hybridization and why it happens. The top diagram here shows carbon's electronic configuration in its ground state. So it's 2s2, 2p2 that you'll be familiar with. Carbon, of course, needs to form 4 bonds and currently only has 2 orbitals with which to form a covalent bond. To form a covalent bond, of course, each atom needs to donate 1 electron. So currently, carbon could only use these 2 orbitals to do so. So that carbon can use all 4, this electron is promoted into the 2p subshell. So the electronic configuration now is 2s1, 2p3, and all 4 orbitals are occupied. So how can carbon form triple bonds, like the ones we see in ethyne, which has got a triple bond between the 2 carbon atoms? Well, we can see that, again, the electrons that carbon has, 1 in each of his orbitals. So 1 in the 2s and 1 in each of the 2p. So 1 in the 2px, 1 in the 2py, and 1 in the 2pz. To form an sp hybrid orbital, as you can imagine, carbon needs to use an s orbital and a p orbital. And the ones that carbon does to do this is the 2s and the 2px. That will leave the 2py and the 2pz not involved in hybridization, but still having 1 electron in each of them. So here I've shown an s orbital, so we have the 2s orbital, and we have the 2px orbital here. And you know it's the 2px because the lobes are along the x-axis. And so these 2 orbitals will combine to give us 2 hybrid orbitals. Remember that however many orbitals go in to form the hybrid orbitals, you get the same number of hybrid orbitals out. So when we formed sp3 hybrid orbitals, we contributed 4 orbitals, and therefore we formed 4 hybrid orbitals. So let's see how these 2 will interact with each other. So when we superimpose the 2s and the 2px on top of each other, you can see that in this area we have constructive interference, but in this area you will have deconstructive because you have the positive phase of the s and the negative phase of the p. This results in the lobe on this side becoming larger, as you can see here, and this lobe becoming much smaller. So for this hybrid, the bonding will occur via that part of the orbital. Equally, of course, the p orbital could have been phased with the plus on this side and the negative on this side. So if this was the case and these 2 combined together, we would now have the larger lobe on this side and the smaller lobe here. You can see that this is where the constructive interference will occur, and this is where the deconstructive interference will occur. So we now have 2 carbon atoms with each having 2 sp hybrid orbitals. So this is one of my carbon atoms, and this would be one sp hybrid orbital. This is the other sp hybrid orbital, and the same for this carbon atom here. And as I'm sure you can see, these lobes can overlap to form my carbon-carbon single bond, whereas the lobes on the other side, this lobe and this lobe, will be ideally placed to form the bond with the hydrogen atom. So on this slide, we've shown the bond forming between the 2 carbon atoms, with the overlap of these 2 hybrid orbitals here, and you still have these hybrid orbitals left to form the bond with the hydrogen atom. So here you can see that the hydrogen atoms have now joined in to form their sigma bonds with the carbon sp hybrid orbitals. So in terms of our single bond framework, we have our carbon-carbon bond here. You then have your carbon-hydrogen bond there, and this carbon-hydrogen bond here, and this is all along the x-axis. And hopefully you can see that these bond angles are going to be 180 degrees here, like so. That will be how the sp hybrids form because of the p only being directed along the x-axis. And so that explains why we have a linear structure around those carbon atoms. So we now have our sigma framework. So now it's time to have a look at how the remaining p orbitals interact. So as we mentioned before, we are left with our py and our pz currently non-involved in any of the fun, but each of these contains one electron, and so they are going to want to bond. So how are they going to do this? Well, first of all, let's put both the pz and the py on the same carbon atom, so we can see how they are interacting with each other. And of course, you can see that they are perpendicular to each other. And remember, of course, that the x-axis is the one where the sigma bonds are. So now we popped the sigma bond arrangement on. Those are the bonds in black. And we've added the other carbon atom as well with the hydrogen. So this again, we've got our sigma framework, and hopefully you can see how the lobes of the pz can overlap with each other and the lobes of the py can interact with each other. So let's have a look at that. So first of all, along the z-axis, we are going to form our pi bond through the overlap of the two pz orbitals. And again, remember, each of these originally contained one electron, so this pi bond here contains two electrons. And slightly harder to see because it's coming out towards us, but I wanted to keep the diagram in the same orientation. You have the py overlap, so going away from you would be a lobe overlapping, and then coming out towards us from the on top of that sigma framework, you have the other lobe overlapping, and again that pi bond will have two electrons, and hence we now have our triple bond as we expected. And we know about why we have our linear geometry around each carbon atom, with the bond angle being 180 degrees. Right, we now had a chance to have a look at sp3, sp2 and sp hybridization on carbon. And our next task will be to look at some other examples to try and relate these ideas to different molecules.